Well, good morning, or good afternoon. This is 12:31. It's supposed to be my Calculus 3 class. I can't get Zoom to return to the meeting. I don't know why it won't go there. It's been scheduled. Everything is here in place, yet I can't get it to start. Let me see if I can figure out what the problem is. Let me try this start. It's in progress. The meeting's in progress, but it won't go to the page. Maybe this is it. We'll go from current slide. Let's see if this works. Okay. I hope we're working now. I haven't seen any students sign in yet. If you're there, please let me know somehow. This is our first time doing this. I did 4 classes yesterday and 1 today, and so far they've worked okay. This one was harder to get into today than the others have been, but I can't tell you why it's harder. But it says we're sharing, it says we're out there. I'm also recording on Screencast-O-Matic, so anything you might have missed coming in late, you can pick up with what you've probably already seen in Screencast-O-Matic. Well, we are in Chapter 12, Vector Value Functions, Section 12.5. Hopefully we'll finish this today. We're almost through with this section. Arc length and curvature, and we're in example 6, bottom of page 860. It says, find the curvature of the parabola given by y is equal to x minus 1/4 x squared at x equal 2. Okay? Now, a couple things when you see something like this. Now, I think I'll need to get my pen set up. Let me do that first. Okay. It says find the curvature of the parabola given by this value. And it says sketch the circle of curvature at 2, 1. And that's what I was just going to say. I was going to figure out what the y value is when x equal 2. So let's do that here. Y is equal to, the pen's not writing well, 2 minus 1/4 2 squared, and that would be 2 minus 1/4 of 4, which is, of course, 2 minus 1, which is 1. So sure enough, this is the right point, 2, 1. That's where the parabola is when x equal 2, the y value is 1. It says find the curvature there. Now, what we had just done, in fact, I think I'll scroll back for people who may have missed last time, because not that many people were there last time. Here is the curvature in rectangular coordinates. If you have y is equal to f of x. Now, if c is the graph of a twice differentiable function, y is equal to f of x, then the curvature k at a point xy, we have that point 2, 1, is given by this. Okay? So there's our curvature. It's at the top of page 860 if you've got your book open. So that's where it was. So one thing we know, we've got to take first and second derivative of this function. So what is y prime? Nobody is logged on yet, so, and my pen is not writing well. I don't know why. Y prime is equal to 1 minus 2 times 1/4 is 1/2 x. Again, the pen's not writing well. Y double prime is equal to minus 1/2. Okay? So there's your y double prime. It is a twice differentiable function. Of course, it would be if it's got a square in it. So there's your y double prime. So what is the curvature? k. Now you'll find me saying kappa a lot because most other texts use kappa. This one uses capital K. And the absolute value of y double prime, which would be 1/2 divided by, open bracket, excuse me, 1 plus, okay, I'm going to write it out here, y prime, my pen is not writing well at all, y prime squared, close the bracket, and that's to the 3/2 power.
Hello?
Oh, somebody's here.
Hey.
Who is it? Patrick. I thought it sounded like you. Okay, did you have any trouble logging in?
No, I didn't.
All right, good.
Frederick's also here as well.
What's that?
Frederick's also here as well.
Who is here as well?
Frederick.
Frederick. Oh, nice. Okay. Now, when you say here, are y'all together or are you just online together?
Online.
I see it. Okay, I thought we should be social distancing, you know, never mind. Okay. All right. Is that all? Fred and Patrick here, right?
Dawson's here as well.
Who is?
Dawson.
Oh, Dawson's here. Excellent. Okay, Dawson's done this before. You're not driving today, are you? You're not driving today, are you?
No.
All right, good. Okay, that's better. He was driving yesterday trying to do it, and I went, oh, I don't want to be responsible for that. Okay. Still missing Ryan and Josh then, huh?
Yeah,
All right.
Ryan is trying to connect, I believe. He sent me a text saying he was trying to connect.
Okay. Did any of you have difficulty getting in?
Nope.
Obviously,
No,
you all got here, but was there difficulty?
No, there wasn't.
Okay, good. All right, then I don't know if you've heard much of example 6 so far, but I got the, here we have a parabola given as y is equal to f of x. The theorem at the top of page 860 tells you what to do, and I've written it down, except I went on and did, this 1/2 came from the absolute value. My pen is just not writing well. There we go. Of y double prime. Okay, so the absolute value of that is 1/2. So that's where this 1/2 came from. Now I just wrote 1/2 and it didn't show up. I don't know. Here's a guess on my part, and I don't know if I'm right on this or not. I think I've just got too much open for this old computer. Okay, maybe for this old instructor too, but I've got Screencast-O-Matic, PowerPoint, and Zoom, and it seems to be bogging down things pretty badly. Yesterday went, I thought, pretty well, but then today it's just been really slow. And now the other thing is, now that I just noticed it, this computer, I've had this trouble in class too, the connection, the power cord connection in the side seems not to connect well sometimes, and it's usually when it gets hot is when it doesn't do well. So I just barely have a faint blue light there. That may be part of it, though I wouldn't think so, but it seems to be, it could be an issue. I don't know. But anyway, the pen's not writing well, so that's why if I say things a couple times, it's trying to get the pen to write. So there's your formula for curvature, capital K, and for those who weren't there last time, some other texts that I have taught from always call this kappa, capital kappa, the Greek letter kappa, which looks a lot like a K, but this book has a capital K. And so if I say kappa, you understand it to be a K. All right, so what we've got to do is figure out what this is. Absolute value of y double prime, that wasn't hard, 1/2. That was pretty easy. Okay, your denominator here, 1, and you see you got brackets and braces here. I mean, parentheses and brackets, okay? 1 plus. Now, we've got to square the first derivative, okay? And the square of that, y prime squared, is equal to 1. Someone else finish this for me. Square that binomial. Earth to class, earth to class.
Wait,
all right.
Is that a y to the negative one?
Okay. No, that's a y prime right there. That's a y prime,
okay.
and it's y prime squared. And here's our y prime up here. This was stuff I had done before y'all got here. I did the first part. 1 squared is 1. I'm proud of myself, okay? What's the next part? Squaring this derivative.
Plus 1/4 x squared.
Okay, that goes at the end, 1/4 x squared at the end. How about the middle term?
Minus x.
Minus x, perfect. Twice the product of the two. Okay, so that's your y prime squared. So let me put that in here. 1 plus 1 minus x plus 1/4 x squared. And then that's raised to the 3/2 power. Okay. There. Okay. Well, I can do that first part. 1 plus 1 is 2. I was been practicing on that one. 1/2 over, well, okay, I'm going to do something else. Well, not yet. I'll wait and do that in a minute. This will be 2 minus x. My pen is not writing. Minus x plus 1/4 x squared. It just isn't writing. There we go. Raised to the 3/2 power. Now, I don't know if they're going to do it, but I'm going to do it. I'm going to get everything over 4 in the denominator. So it's going to be 1/2. Now I wrote too much. Okay. 1/2. Okay. With 4 as the denominator, it would be 8 minus 4x plus x squared all over 4. And that everything is to the 3/2 power. Okay. Not a lot better, but I found it a little better. So what I'm going to do now is take the square root of the 4, which is 2, and cube that, and that becomes an 8. And because that's in the denominator of the denominator, that's like in the numerator. Okay, so 8 times 1/2 is 4. Now that was a lot sleight of hand there. I hope you didn't get too confused by it. Is that okay? So I wiped out that denominator down here. It looks like I just moved it upstairs and got rid of my 1/2, but I didn't. Okay. Now, we still got to I really regret that 8 minus 4x plus 1 plus x squared is not a perfect square. If it was, this would be a much easier problem. Okay, but it's not, and we're not asking for the curvature everywhere. We're just asking for the curvature at 2, 1. And that is on this parabola. We already confirmed that. So let's just do the curvature at point 2, 1. Okay? And this only has x's in it. There we go again. So we just plug in a 2. Okay? So this will be 4 over 8 minus 8, that's pretty handy, isn't it? Plus 4 Okay, so that's all we got in the denominator, 4 raised to the 3/2 power. Well, okay, the square root of 4 is 2. 2 cubed is 8, so this is 1/2, 1/2. And that's the kappa, K that they had. Now, that was a little bit on the dumb side of me, because frankly, since we're only interested in the curvature at that one point, we could have plugged in the 2 here, and here, of course, that there isn't even an X there, and we could have plugged them into the formula right like that and saved ourselves a little bit of grief. But I was expecting them to do a little bit more with the form, but they didn't ask for anything more. Oh, except sketch the curve, the circle of curvature at 2, 1. Well, that may be a bit more challenging. Okay, so I'm going to erase most of this, but remember your curvature at 2, 1 is 1/2. Okay, so I think I'll go on and wipe out all of this. Okay, and the kappa at K, capital K at 2, 1 is 1/2. Now, notice that's a circle of curvature. Can anyone tell me the radius of that circle? Now that's at a point 2, 1. It's not at, don't get anything confused. What is the radius at that same point? Anyone make a guess? If you turn back to example 4 on page 858, you'll see a formula that'll be helpful there. For any circle, curvature of a circle of radius r, what is the curvature? If you got your books, flip back just one.
It's the magnitude of t prime of s.
Whoa. Go down. Example 4, underneath that. Show that the curvature of a circle of radius r is, you see that line?
K equals 1/r.
Exactly. And if K is 1/r, what is r? K is 1/2?
So r is 2.
R is 2. All right. We know the radius is 2. Okay. It says sketch the circle of curvature at 2, 1. Okay. Now I think what I'll do is sort of draw, when I say sort of, I mean sort of draw my graph here. Now we already, we haven't done this necessarily, but at x equals 0, you're at 0. At x equals 2, you're down here at 1. We know that. There's the point. We already verified that earlier. Okay. My pen is not working well. Okay. When x is equal to, say, 1, that would be 1 minus 1/4, so that would be 3/4. Well, it would help if I wrote the 1 in the right place. There's +1. Okay. Not down here. Okay. Sorry. So 0, 0 is on the graph, and 2, 1 is on the graph. And 1, what do we say, 3/4 is on the graph, something like that. And let's, just for funsies, do 3. 3 minus, well, 3 cubed is 9, right? 1/4 of 9 is 2 1/4. So 3 minus 2 1/4, I'm pretty sure is 3/4 again, isn't it? I think I see where this is going. Okay. At 4, I bet you it's 0. Because it looks like this is our vertex of this parabola. You know it's a parabola. You know it's opening downward because the leading coefficient is negative. And it's got to be symmetric. And that seems to be the vertex there. Let's just see if you plug in a 4. 4 minus 1/4 of 4 squared, that would be 16. 1/4 of 16 is 4. 4 minus 4, sure enough, is 0. Okay. So we're interested at 2, 1, which happens to be the vertex there. Radius of 2, so since we know that's a vertex, the radius, the center of this circle must be right there at -1. Are you following? Because the radius is 2, and the radius has to be along this line. Since this is a parabola, everything is symmetric about there, including the circle inside. So the next point here would be 4, 1, and 0, 1, radius of 2 everywhere, and this would be, I'm sorry, I said it backwards, 2, okay, 0, 1, the center is 2 below here, so that's at 2, -1. So another point on the circle would be another radius on either side of that. So 0, -1, and 4, -1. And then down here at 2, -3. So here is the circle. I don't draw circles well at all, but that's basically the circle you have. The parabola does something like this. I don't draw parabolas well either. The circle fits right inside of it. Mine doesn't, because mine is not a very pretty circle. But that's what you got. If you've got your book open, you see a much better rendition of that circle. We use the fact that of any circle, the curvature of the parabola at that point is 1/2, but this circle of curvature has the same curvature as the curve does, and so that's also 1/2, and that makes the circle of radius 2. It fits up in there very snugly if you look at the one in the text. Okay? Any questions on that? That's how we did it. Oh, we get to see how they did it. I forgot. This one's going to be given here. The curvature at 2 is as follows. Y prime is equal to 1 minus x over 2, or 1 minus 1/2 x is how I said it. And then when you plug in x equal 2, you get 1 minus 1, which is 0. Y prime at that point is 0. Y double prime is -1/2, so y double prime is -1/2. Then your curvature is the absolute value of the second derivative, which is 1/2, divided by 1 minus y prime squared to the 3/2 power. Y prime is 0, so it's 1/2 divided by 0. That makes it a little bit easier to do than the way I did it. Okay, so your curvature, capital K, is 1/2. And then from the fact that it says sketch the circle of curvature, that means the radius of that circle, because the curvature at that point, 2, 1, is 1/2, it follows that the radius of the circle of curvature is 1 over that, which is 2. And so the center is 2 units below 2, 1. That would be 2, -1. And then you go to the right 2, that would be 4, -1. To the left 2, 0, -1. Down 2, which would be 2, -3. So those would be the 4 points that define that circle. Okay? And then do your best to draw them. The parabola is the darker line. The circle of curvature inside that parabola is what's given there. Now I've got a question for you. Is this the smallest circle of curvature, largest circle of curvature, or a medium circle of curvature for the rest of this parabola, if you were to draw it? What would be your guess? Any guess? Anybody there?
Larger one?
No, this is actually going to be, all the rest of them will be larger than this one. This will be the smallest one because at the vertex, even though this is a pretty broad circle here because your coefficient is 1/4, you know, negative 1/4, this is the smallest circle of curvature you have. You see out here, if you come on out this way with the parabola, that's almost a straight line. That circle of curvature is huge. Same thing down this way. Okay? Circle of curvature would be huge out there. Much bigger than what I just drew. This is the smallest. At the vertex of a parabola, that's where you have the greatest curvature and the smallest radius, therefore, and also the smallest radius. So curvature is the smallest circle. So yeah, this will be the smallest one that parabola will have, because that's always at the vertex. That was beyond what they're asking for here. I just threw that in. Okay. I think that's through with example 6. Oh no. In the figure, note that the curve has the greatest curvature at P, the smallest circle at P, because the greatest curvature is the smallest radius. Okay, I hope I asked my question correctly, but that's what I was trying to get at. Smallest radius because it's the largest curvature. In fact, it's turning more quickly there than it is anywhere else. All right, moving on to page 861. Were there any questions on that before we left it? Okay, I could hear the head shaking no, so I figured that was a no. Okay, I heard one no, by the way. Theorem 210. Now that is an unusual. Oh, I think I know what happened. I think when I was setting up this thing, I thought I was saying that I should see your picture. The way they asked the question, I think it took your picture off. So that's why I can't see you when you say something. The other classes I have been able to do that. I can't now. I couldn't see Dawson yesterday because he was driving, so you were probably on the phone too, weren't you?
We yesterday. Have the option to show our face.
What's that?
We have the option to either use the facial camera or not.
Right. Can you see mine?
Yeah, I can see yours.
Oh, I'm so sorry. Okay. But I can't see yours, and that option was there at the beginning. I thought I left it on, but evidently I must have turned it off by mistake. So, but that way, that's why I can't tell who's there. So if anyone else comes in, please let me know. Of course, that I'm only talking to people who are here now. No one knows if Ryan's in yet, huh?
No, he's still not
here. Not okay. How about Josh?
He's not here either.
Not here. Okay. So let me know if either of those seem like they show up, because I can't tell now. I messed up there. All right. So anyway. This is Theorem 1210, dealing with curvature, but now we're going to deal with acceleration, speed, and curvature. Theorem 210. If R of t is the position vector, not just any old function, for a smooth curve C, then the acceleration vector is given by, A of t is equal to the second derivative of your arc length parameter, that's that S, remember? d2s dt squared times the tangential vector. Okay, now what that is, that's your ds dt is your speed. So this is the first derivative of your speed, okay? Second derivative of your arc length parameter. Plus your curvature, K, I want to say kappa, but K, times ds dt squared for ds dt, and here it is. ds dt is the speed, okay? K is the curvature, ds dt is the speed, and the the second derivative of s with respect to t squared would be your first derivative of the speed as a function of time in terms of the arc length parameter. So it makes for a pretty simple looking formula, okay? One is actually a second derivative, the other is a first derivative squared. So they sort of look like they would balance each other somehow, but the second one has a 1 over, well, it has the curvature in front, okay? They do a little proof here. Let me see, I don't think the slideshow does that. It was, you can go through the proof if you'd like. It bases this back on your the tangential component of your acceleration, which indeed was this, okay, and your normal component of your acceleration, which we weren't using k back then. We were using something else, and they give it down here, magnitude of v times magnitude of t prime, which is sort of a pain in the neck type thing to do. But anyway, you can look at that proof and see that it does come from that. So let's move on to example 7. Find your tangential component of the acceleration and the normal component of your acceleration for the curve given by this. So how would you begin? Take a derivative is always a good answer, isn't it? Okay, r prime of t is equal to this is where y'all come in. And the t didn't show up. There it is. R prime of t is derivative of 2t. Help me, somebody. Is anyone still there?
Is it t squared?
No, derivative, not integral.
Just 2 then.
2. 2i.
Goodness
gracious, yeah. The pen not only is not cooperating, it's drawing different things from what I'm drawing, okay? And I think it has to do with I've got too much loaded on the old computer now. It's there, that's a little better, okay? Next, you said 2tj, is that what you said? Say yes, okay, good. And then? Minus t squared k. All right, good, we got that done. Now,
now we need to take a magnitude of that.
Yes, and why that? The magnitude of this is the speed of the object that's moving on that curve. And the speed of the object is your ds dt. So we do take the magnitude of this. And what would that be? I'll start it off for you. Four plus 4t squared. Is that what I heard? Plus t to the fourth. Okay. There's your r prime of t, the magnitude of r prime of t. Okay? And the good news is that's a perfect square trinomial, isn't it? What is that? That was the 2 plus t squared squared. And the square root of that would just be 2 plus t squared. And because that is the magnitude of r prime of t, that is also your ds dt, which is, well, just stop there. It's ds dt. That's your speed. Okay, dSdt is your speed. The magnitude of your velocity vector is your speed, because this is the velocity vector, v of t. Okay, and the magnitude of that is your speed, and that's dSdt. Now, are we there yet, you might say? What we're looking for, a sub t and a sub n. Does this give us either one of them? The answer's no. Okay. But what does this give us? This gives us ds dt, right? And what can you do with that? Take a derivative again. Well, yeah, you're going to square it later. You're absolutely right. But right now, let's take a derivative of that. d2s dt squared. That's just taking the second derivative of this. There's the first derivative, is that. What's the second derivative? It's not that hard. 2t. All right. Does that give us anything worthwhile? Please say yes.
That gives us the t.
The what? The tangential component of your acceleration vector. You're absolutely right. There we have half of it done. Okay? Now the second part is, of course, as you said, we are going to want to square this, so let's square that. ds dt squared. What would that be? Y'all did so well on the last one. 4 plus 4t squared plus t to the fourth. I mean, correct me if I'm wrong. My pen is just not writing. It writes some and then just leaves off others. I don't even know what part that was. I think that was part of the 2, but it's just not writing it. I don't know what's going on here. It's t to the fourth, but I can't get it to write. Okay, let me try it again. I've never had this much problem with the pen. T to the fourth. Okay, except that's just a t, it's no 4 there. The whole screen, I mean, I think I'm beginning to guess now that Screencast-O-Matic does not like Zoom. They're not getting along well at all. Now here's what I was going to say. This thing here is just the integrand there. I mean the radicand there. That's all it is.
I'm here. Do I get marked as attendance?
What's that again?
I was just saying, like, Ryan's here.
I thought that might be it. Okay, Ryan's there? Is that what you said? Okay. I can't see because I must have hit some setting so it's taking your pictures off of here, which may be for some people not a bad thing, but no, I didn't say that, did I? Okay. All right. So we got our ds dt squared, but what are we still missing? K. If we only had K, we'd have it made. Okay? Now, does anyone recall how we can get K? Now, don't go to Theorem 12.9. That was for a twice differentiable scalar function. We have a vector function here. Don't go there. Okay? If you back up a little bit further, you have a couple of other definitions for K, and none of them really look all that useful. And of course, there's a reason for that, because they just went back to example 5, which had this same problem. Okay? And I don't know if you've got your books in front of you there. If we recall, and you may or may not recall, Example 5 took a long time to go through. Okay? We finally got there, but at that point, and it was the same vector function here, exactly the same vector function as we have here. Okay? And the k from back there was, this is capital K. Look at that. It's just nuts. Is not even drawing my equal sign. There's one of them. There's the second one. Okay. 2 over, it just writes parts of it. T squared. And it doesn't do a good job of writing any of it. It's kind of like the pen is on drugs. Okay. I can't even get the eraser to come up now. I'm telling you, Screencast-O-Matic is getting sick and tired of this new boy on the block. Okay. I'm going to start over. I'm sorry. Okay. Try this again. Writes the first part and then writes the very last part, leaving out the middle part. Okay? Over t squared plus 2 squared. Just writes part of the 2. And now it messes it all up. I did not write it that way. That's how it did. And then it brought all this other junk in there too. So there's your K. All right. Now, I want you to notice something. This right here, the square of this is that, right? And we're going to take K, which has this very same denominator here, squared, right? So guess what? When you multiply, let's see if it'll write. Hey, it's writing okay now. I shouldn't say anything. A sub unit normal vector, that was a hat, and it became a straight line. I don't know how, okay? This is equal to what we had before was capital K, which did not write at all. And what it did write doesn't look anything like a K. Okay. Huh. This is totally nuts. Okay, that's your capital K times D S D T. Maybe I'll just write slower and it'll do. Squared. Okay. I'm also writing bigger. Okay. The K is 2 over T squared plus 2 squared times ds dt squared, which is, I'm going to go back to this and just write it as t squared plus 2 squared, right? That's what it was. You square this and you get that. Well, guess what? Those two go out. Your a sub n, the normal component of your acceleration vector, is the number 2. And that's all, folks. Just 2. Whew. The only hard part was getting the pen right. The calculus part was easy. Any questions on that? Now, admittedly, this was a hard part. Okay, look at that. I drew a circle all the way around it, and it just went from here to there. I don't know why. But anyway, that's to get that took us probably 15 to 30 minutes last time. Okay, I'm glad we didn't spend that time again. All right, any questions? Let's see how they did it. Can I erase? I hope all the heads are nodding yes. I don't hear anything. So let's erase. And from example 5, that's all they did. They went to example 5 and they said but it was pretty easy to do. We found out what r prime was, and then we took its magnitude and got t squared plus 2. And kappa, or k, capital K, was 2 over t squared plus 2 squared. Okay? Now, what you do to get a sub t is take the derivative of this one, which is 2t. Done. That's the tangential component. And what you do to get the normal component is take your capital K that we already had and multiply it by this thing squared. Okay? Well, if you square that, you wipe out your denominator, because then they're both squared, and that's equal just to the 2 over t squared plus 2 squared times t squared plus 2 squared. And the t squared plus 2's squareds go out, leaving you just the number 2. There's your normal component. If only they could all be that easy or simple as an answer. Not easy to get there, because the steps that it took to find this were not bad. To find this, that took a while last time. And they are practicing conservation of energy. Okay. So there's example 7. Now we look at an application. There are many applications in physics and engineering dynamics that involve the relationships among speed, arc length, curvature, and acceleration. One such application concerns frictional force. A moving object with mass m is in contact with a stationary object, like a tire on a road, okay? The total force required to produce an acceleration a along a given path is F is equal to ma. To produce that acceleration, multiply by the mass and you get that force. Well, from what we just did, that would be mass times, here's your tangential component of your acceleration times your unit tangent vector, plus m times your curvature times ds dt squared. That's your coefficient of your normal component of the normal unit normal vector is what I'm trying to say. So that's m times a sub t, the tangential component of your acceleration, times your tangential unit tangent vector, plus m times a sub n, the normal component of your acceleration, times your unit normal vector. The portion of this total force that is supplied by the stationary object is called the force of friction. Now, that's a mathematician's way of expressing a pretty decent physical concept, okay? I'm not sure Dr. Bryant ever expressed it quite that way, but it could be said that way. For example, when a car is moving with a constant speed, rounding a turn, the roadway exerts a frictional force that keeps the car from sliding off the road, okay? If the car is not sliding, the frictional force is perpendicular to the direction of motion and has a magnitude equal to the normal component of the acceleration, as shown in this figure here. Well, let's go back to here. Okay. I'm not certain I'm comfortable with their wording here, but we'll say it's okay now. Okay. Here's what I think they're trying to say here, though I don't know. This is the force that tangential to the motion of the car. This is the force that's normal to the motion of the car. The tangential force is what's, if anything, increasing your speed. We've found that the speed was constant, so that part's going to be 0. So the normal part, the part that's pulling it into the curve, if you were in physics, they would call that the centripetal part of the force. That's supplied by friction. So I think that's what they're trying to say. The reason I hesitated this, what's pushing you forward also depends on friction, okay? But it's the friction that keeps you from, that forces you into the curve. That's all friction, okay? For example, when the car moving at constant speed is rounding a curve, the roadway exerts a frictional force that keeps the car from sliding off the road. If the car is not sliding, the frictional force is perpendicular to the direction of motion and has a magnitude equal to the normal component of the acceleration, shown in this figure. The potential frictional force of a road around the turn can be increased by banking the roadway. Okay, now it's not clear whether that one's banked or not. Okay, the way they drew it, it's not banked because now the force of friction is just supplied by the road. They haven't indicated the bankingness of it yet. Okay, so here we have a 360 kilogram go-kart, 360 kilogram go-kart, driven at a speed of 60 kilometers per hour around the circular racetrack of radius 12 meters, shown here. Okay, got it. To keep the cart from skidding off the course, what frictional force must the track exert on the tires? Okay, to keep it from sliding off the course. Okay, now what we're looking for now, going back here, is this component right here. That's what we're looking for. Okay, now this ds dt, remember that's the speed. In this problem, that's the speed. ds dt. Okay? Okay. Curvature. We need that curvature. What is the curvature? Anyone help me with that? 1/12, because the radius is 12 meters, then the curvature is 1/12. The unit there would be per meter, okay, if you were keeping up with units. And then, of course, the mass is this. Now, does anyone see any kind of little problem with this setup? I'll give you a hint. Units. Any? Did someone say something? I thought I heard a squeak.
60 kilometers and 12 something.
Okay, yeah, you got 60 kilometers per hour. You got 12 meters. And the all right, I'm trying to see if they say anything else about any other units. Most of the time, the unit you want to be dealing with is seconds, not hours. Okay, so my gut feeling is we need to get that 60 kilometers per hour down to meters per second. Now, let me see if the book did that. Yes, they do. in a strange and weird way, they do. So let's us do it a bit more reasonably. This is a math book, by the way, not a physics book. 60 kilometers per hour. That's what the speed was. Okay? Okay? Or let me actually call it dsdt, since that's what we're going to be using anyway. dsdt. That's it. Okay? But let's multiply that by one set of conversions, maybe by another set, possibly even by a third set, and we're trying to get so many meters per second. Okay? Now, if any of you have been in any of my classes before, you probably recognize this way that I do unit conversions. If you haven't, this may be totally stupid looking to you. Okay, but what I have here, one blank is for numbers, one is for units. Numbers, units, numbers, units, and of course numbers, because we already got units here, got numbers and units there. Okay, my mantra is always put the units in their place. Don't worry about numbers yet, always put the units in the place. So you decide, are you want to convert kilometers to meters or meters to kilometers? I mean, kilometers to meters first, or do you want to convert hours to seconds, or maybe something in between? You choose what you want to do first. It doesn't really matter. Kilometers to meters. So you choose which, above or below the line, kilometers going to go one place, meters going to go another. You tell me which goes where.
Meters on top.
Meters on top, kilometers on the bottom. Okay, Patrick's been in my class before. Okay, now you answer the question, how many meters in a kilometer or how many kilometers in a meter? Now we fill in the numbers. What would that be? Help me, somebody.
1,000 meters.
1,000 meters is 1 kilometer. That's what K means. Kilo means is 1,000. And now what we can do is wipe out our kilometers, and we're going to have meters just where we want it. So let's get to our time units. Your hours, and you're trying to get the seconds. You want to go in one step or two step? You decide. What can you convert hours to easily?
Minutes.
Minutes? Is that what I heard? Well, which is going to go where? One goes on top, one goes on bottom. Hours. Which one?
Hours on top.
Hours on top, minutes on the bottom. Okay? And then you answer the question, how many hours in a minute or how many minutes in an hour?
That's
60 minutes is 1 hour. Perfect. Now you can cancel out hours. They're out of there. But you're still, you got meters where you want it, but you got minutes down here. We need one more conversion. What's that?
Seconds and minutes. So minutes on top.
Minutes on top and seconds on the bottom. Then you match the numbers with the units. What would that be?
60 seconds.
60 seconds is 1 minute. All right. Now we can cancel out the minutes. And we wind up with meters per second, exactly what we want. And the good news is, one of these 60s will wipe out one of those 60s. Okay, that'll be good. And one of these zeros will cancel out one of those zeros. So now we have, and actually you could do 2 into 6 would be 3, and 2 into 100 would be 50. So 50 divided by 3 would be something like 17.7? 7 or 66666 or 16.6667.
Yeah, that one's
right.
16.667.
Okay, 16.667. That's way more digits than we need, but we're okay with it. Okay, so that's your meters per second. All right. And that's your dsdt. All right, let's go back and remind ourselves what the formula is now. It's m times k times speed squared, right? Okay. So your m here, this is your a sub n is equal to m 360 kilograms, k is 1/12, and this is a per meter. So I'm going to put the meter down here, okay? Times the SDT squared. So that would be, I'm going to go back and do it this way. 50 over 3 meters per second squared. Okay? You okay with that? All right. I know 12 will go into 360 30 times, right? So I wiped out that one. That's going to give me 30 kilograms times a per meter. That's just a unit, 1 per meter, okay? Times 2,500 when I square the 50, and 9 when I square the 3, and this will be in meters squared per second squared. Okay? Well, this meter is going to wipe out one of those meters, and what you have then is a kilogram meter per second squared. Does anyone recall what that is? Kilogram meter per second squared. Those who have had physics ought to recall this. No, it's a Newton.
It's a Newton.
Newton, exactly. Let's see if we can get our units to do a little better. 3 will go into this 10 times. 3 will go into that 3 times. So we have 2, boy, big number. 250,000 divided by 3, which is something like 8, 1. I'm doing this in my head and it's awfully slow. 81.11111. That can't be right. Someone do that. 25,000 divided by 3. 25 divided by 3 is 8.33. 83, huh?
833.
833. Okay. We'll round it just like that. Newtons. Okay, I'm pretty sure they didn't use a unit. Oh, one more 3 there. I thought I needed one. Okay. 8,333 newtons. Is that right? Yay or nay? Because don't forget your 10 over here. I think that's where the extra digit came from. All right. Kilogram meter per second squared, which is a Newton, by the way. But he's a mathematician. He doesn't know that. All right. Any questions on that? That seems like a lot of force. What frictional force must attract surface exert on the tires? That's a pretty hefty amount. I think I'd slow down if I was that kid, or whoever it is. Okay. Any questions? Let's move on to, continuing example A. The friction force must equal the mass times the normal component of the acceleration for the circular, this is just showing, we did it, here's how they did it. For the circular path, you know the curvature is 1 over 12, exactly right, circle. Frictional force is A sub n is mass times curvature times speed squared. So that's going to be 360 kilograms times 1 over 12 meters times what they did. Goodness, talk about a weird way of doing this. They took their 60 kilometers per hour, made it 60,000 meters per 3,600 seconds, squared both of those. I can't imagine what their calculator looks like. Huge numbers. And anyway, magically came up with about 8,333 kilogram meter per second, which, by the way, is a Newton, which is a force. Okay. Now, your page 863, here's the top half of that summarized. velocity, acceleration, and curvature. Unless noted otherwise, let C be a curve either in the plane or in space given by the position vector either r of t is x of ti plus y of tj or r of t is x of ti plus y of tj plus z of t k, plane or space. Okay, where x, y, and z are twice differentiable functions of t. Okay, so your velocity vector is v is r prime of t. Pretty simple. X prime I plus y prime j, or x prime 1 I, x prime I plus y prime j plus z prime k. That's your velocity vector, first derivative of your displacement vector. Magnitude of that is r prime of t, magnitude, which is exactly ds dt, always. Okay, a lot of things in arc length parameter are not particularly easy to deal with. This one is. Your acceleration vector is r prime of t, okay? And you can either write that in terms of I, j, and k, and that's pretty straightforward, or you can write it as a sum of your tangential component of your acceleration times your unit tangent vector plus the normal component of your acceleration times the unit normal vector. But to get that in more useful terms, that's d2s dt squared times your unit tangent vector. That's the first derivative of your speed, okay? And that's in the tangential direction. And then your curvature times ds dt squared as your unit times your unit normal vector. Okay. Now, what are those unit tangent and principal unit normal vector? The unit tangent vector is merely your r prime of t divided by r prime, the magnitude of r prime of t. It's got to be in the direction of your tangent, okay? That's r prime of t, and it has to be magnitude 1, so you divide by the magnitude of that. And what is a unit normal vector? It's the derivative of your unit tangent vector divided by its magnitude. Now, those are pretty simple formulas to write down. They can be a bear and a half to do, because anytime you're taking a magnitude of a fairly complicated vector, which is a derivative of your unit tangent vector, can be pretty complicated. That's a mess in itself. However, there's some easier ways to calculate these. d2s dt certainly is one way to do the acceleration, the tangential component of the acceleration. But another way is a dot t. Well, t is pretty hard to get to, so let's do v dot a divided by magnitude of v. Okay. V dot a is the magnitude, and because the dot product gives you a magnitude, and magnitude of v gives you that. And that is going to be your first derivative of your speed vector. Okay. Your unit normal, your normal component of your acceleration is a dot n, but normal vector is a hard thing to do, usually. So a shorthand for that, because the v is really easy to get, the a is pretty easy to get, so v cross a, if you look at the comparison here, here's v dot a over magnitude of v, here's magnitude of v cross a over magnitude of v. I mean, they really look like they're somewhat similar. They're not, but they really look similar. But this still can be, kind of a messy thing to do, because this is going to be a three-dimensional vector, perhaps. This is a three-dimensional vector. You've got to take magnitudes of both and divide them. Sometimes a far easier thing is just your acceleration vector, which is easy to calculate. Second derivative of your displacement vector. That magnitude squared minus the square of your the tangential component of your acceleration vector, which you've already calculated. Okay, just square this, subtract it from your original a squared. And this, when you do all that, that gives you your curvature times your speed squared. Okay. Whoa, then let's go to the curvature. If you've got a function, your curve is just defined in a plane, okay, y is equal f of x, then just the absolute value of your second derivative of y divided by 1 plus the first derivative squared, first derivative of y squared, that 1 plus that raised to the 3/2 power, that's your denominator. Your numerator is y double prime squared, magnitude of y double prime, absolute value of y double prime. Okay? If y is a function of x. But if you have a vector rendition of that, where your c is given as x of ti plus y of tj, now this again is in the plane, then it's x prime y double prime minus y prime x double prime, absolute value of that difference divided by x prime squared plus y prime squared, and that's raised to the 3/2 power. Okay? Now, just a few similarities here, kinda. The y prime squared and that to the 3/2, those are all the same in the denominator. It's just this one has an x prime squared in front, not a 1. Okay? And it's kind of like, without having the x of t in there, well, I can't think of any way to make it simpler. I mean, I can see some mnemonic devices, but I can't see anything that makes sense to do it. So, how about curvature in the plane or in space? The plane was up top. These are formulas for plane or space. The magnitude of your first derivative of your unit tangent vector. Okay. Now that's an arc length parameter. Okay, which is not always an easy thing to get, which would be r double prime magnitude in arc length parameter 2, magnitude of that. Or if you're not in arc length parameters, it's the magnitude of t prime over r prime, both magnitudes, but that t prime could be expressed as r prime of t cross r prime double t, or double prime of t, I can't say things right, magnitude of that over r prime cubed. Okay? Or, the other way is a of t dot product with the n of t over v of t squared. Now, magnitude of v of t squared. Now, for the life of me, I don't know why they went from r primes to v's. Those are the same thing. But I guess if they have acceleration vector, they'll do. But you see, it looks like to me this would be very simple to write as magnitude of v of t cross a of t over magnitude of v of t cubed. Okay? Now, if they were going to write this one with a's and v's, why not write that one with a's and v's too? I don't know. Don't know why they did that. Cross product formulas apply only to curves in space, not to planar curves. Got to have 3 dimensions to do a cross product. That ends 12.5. Thank goodness. Okay. Homework exercises here. Okay. They include, now always look at the concept checks. Those are good to look at no matter what. Your homework exercises then, though, would be any of the odds 3 through 9. They're all at Calc Chat. Any of the odds 11 through 15, they're all at Calc Chat, with 13 being at Calc View. 17's at Calc Chat. 19 and 21 are both at Calc Chat. 21's at Calc View. 23 through 27 are at Calc Chat. 29 to 35 are at Calc Chat, with 33 being at Calc View. 37 and 39 are both at Calc Chat. 41 through 47 are at Calc Chat, with 43 at Calc View. Okay. 49 to 53 are at Calc Chat. 55 or 57 are at Calc Chat. 59 is at Calc Chat. That's an exploring concepts type problem, so you can explore that if you want to. 61 and or 63 and or 65 are all at Calc Chat. 67, or I'd say any of the odds 67 through 71 are all at Calc Chat. 73 is at Calc Chat. 75 is a proof. You can do that. It should be at Calc Chat if you like. And then any of the odds 77 through 81 should be at Calc Chat. 83 and 85 are true false. You can look at those two. They should be at Calc Chat. And here's a thing, blurb on Kepler's laws. I think we talked about that some. 87's, well, 87 through 93 are all proofs. So I'll let you decide whether you want to go with those. Now, if you haven't had enough to work on, and you do have spring break coming up, remember the bad news, good news situation. The good news is next week's spring break, but the bad news is we won't be meeting together. I'm sorry, okay? So you might want to do a few review exercises just to keep yourself sharp. And again, they don't have any at Calc View. They're all at Calc Chat. 1 or 3, 5, 7, 9 or 11, 13, 15, 17, 19, 21, 23, 25, 27 or 29, 31 or 33, 35, either 37 or 39, 41, 43, 45, either 47 or 49, 51, 53, 55 or 57, 59 or 61, 63 or 65, 67, 69 or 71, and 73. Okay, is that enough? There are some additional problem solving given, and these odds are also at Calc Chat if you're really interested in them, and you can do any of those odds, 1 through 13, I think. Okay, and that finishes chapter 12. Now, here's a question I have for you. Is anyone who's out there listening still awake? No, that wasn't the question. Did not get your test on chapter 12?
I don't have it.
And
a paper copy.
And what?
I don't have a paper copy of it.
And who is talking?
That's me, Patrick.
Patrick, okay. So you didn't get a paper copy. I thought I passed this out last time you were there.
He left too early.
Oh, Patrick left early?
Yeah.
Oh, I see, okay. How about Ryan? Did you get one? Is Ryan still there?
His screen's still there, but I don't think he got one either.
Okay, I didn't remember him being there. And Josh didn't either, but Josh hasn't shown up, has he?
No, he's still not here.
Okay, so I think I'll do one to Ryan, Patrick, and Josh. Now, it'll probably be this evening before, at the earliest, before I'll be able to, what I have to do is scan those, get them in PDF format, and attach them to emails. I'll try to do that through Blackboard, but this new Blackboard, I haven't done that on it yet, so I'm not sure how easily that will do. I've heard horror stories of people trying to do things in Blackboard, the new version. Yeah.
Are we going to turn in our test through Blackboard?
Yes, yes, you can either turn it in through Blackboard or attach it to an email and send it to me. You know how to do it through Blackboard?
Not quite.
Supposedly you can get that kind of information if you go to the Lawson State webpage, you know, there's a series of blue tabs at the top of the page, sort of 2 rows of them. But then sticking out there somewhere is a bright gold one, says quick link, I think it is, right? If you go to that one, there's a student portion of it, there's a faculty portion. Somewhere in the student portion is everything you could ever want to know about Blackboard, I think, or something like that. That's what the dean was telling me this morning. If you can't figure it out, just send it to me by an email and attach it to the email. Okay?
We also turn in our research papers the same way?
Same way, exactly. Now, here's the deal. They say we're coming back. We have this week, which today's our last day. Next week is spring break week, tears and gnashing of teeth. Okay, and then the following week, we're also online. Okay, well, after that, they think we're coming back. If you want my thoughts on it, which aren't worth anything, I think there's no way in the world we're going to be able to come back that week. I think the numbers are still rising and probably are going to rise at an increasing rate. Now, I don't know if y'all have heard any differently from that, but my wife's an infectious disease epidemiologist. She's been tracking it on whatever that big hospital is, outpatient clinic in, I think in Baltimore or somewhere, really well known. I can't think of the name of it now. She's been tracking the data from that, and we're still on the upward curve of this. We have not even begun to level off, I don't think. So I don't think in 2 weeks we're going to be ready to go back to campus, or 2.5 weeks or whatever. But we'll see. So I would say go on and send the stuff through as a link to, as a attachment to an email or through Blackboard. If you do it through Blackboard, please let me know so I'll know to go and look for it there. I know where to look on my email, but I'm not absolutely certain I've ever gotten one off Blackboard. So I'll have a learning curve there too. Especially this new Blackboard, I'm almost certain that I haven't done one off of it. So yeah, do it either way. Now the reason I say that helps me get them graded sooner and also helps you see your score better. And remember, if you get the paper in during the month of March, which is not that much left, and part of that spring break, you do get 2 bonus points. In the first 3 weeks in April, you only get 1 bonus point. So to get that extra bonus point, you've got to send it through email or Blackboard. So get it to me one way or another. All right, does that answer those questions?
Did you answer the question on the test?
What about the test?
Where will we be turning that in?
Yes, you can turn in the test the same way. Either attach it to an email or attach it to Blackboard. But if you attach it to Blackboard, be sure to let me know you've done so. Okay? That's both. Are you talking about the first test or second test?
We have a second test.
All right. That's what we're just talking about, I think. Okay, the first test was given way back in February, and 3 of the 5 of you have turned that one in. Okay, the second test was given, was it Monday?
Yes.
Okay, Monday. And that is the one we're talking about that I'm going to email at least 3 of you, Ryan, Patrick, and Josh. I'll either send it through Blackboard or through email. I think probably email, but I've got to see which works easiest. So be watching for it. That's the second test. which leads to the point of get that first test in, okay, because you've already given you the second test. And also, get those research papers in, because this, of course, one of my best classes of all time, I haven't gotten a single research paper in yet. So please get those in. All right, good deal. Any questions? Other questions? All right. We've still got about 15 minutes, right? 13 maybe? You still there? Oh, everybody went home, huh?
No, we're
still there. Okay, you are home. Okay, I got it. I'm trying to, there we go. Find a way to get out of this. Now, the last class, when I went to do something like this, the screen sharing stopped because the shared window, and now I can see Ryan. Hey there. Okay. And I couldn't get it started again, but I'm going to try to do that now. And let me go to Power. I think what I do by mistake, I must have closed PowerPoint. I didn't mean to. I meant just to get out of it. So let me, I've got to go back and get PowerPoint open. Is it here? Yeah. And this was doing this last time too. Larson Calculus 11, that's it. And I need to get to 13.1. Yeah. Okay. And we'll go to current slide. And now, I can't do that yet. I think I go back to Zoom. This is where I'm having trouble. Okay, return to meeting. Oh, there's Ron again. Okay. Share screen. Hey. And I'll go to this one. That's what I didn't figure out to do last time. So hopefully you'll be able to see this one. My last class I couldn't get it back to, but let's see if you can.
Yeah, it's working.
I'm not there yet. It's still trying. Okay. There.
We can see it now.
You can?
Yep.
Excellent. Okay. So here's chapter 13, functions of several variables. Okay. And 13.1, you're going to introduce you to functions of several variables. Okay. Objectives here, there's a bunch of them. I've got Fred on my screen here. Do you have anything for me, or you just pop up for some reason?
I guess I just popped up.
Okay. I'm going to move you up to out of the way here. Okay. You're not in the way anymore. All right. Understand the notation of a function of several variables. Yeah, that would be important. Sketch the graph of a function of two variables. Ooh, that may be a little more challenging. Sketch the level curves for a function of two variables. Okay, that is sounding more interesting. Sketch the level surfaces for a function of three variables. And we'll use computer graphics, yes we will, sure, to graph a function of two variables. You may do it, I don't have them, okay? So let's look at functions of several variables. What we've done so far in our calculus life is we know only the functions of single independent variable. Y is equal to f of x. X is the independent variable, y is the dependent variable. But many familiar quantities, however, are functions of two or more variables. Here are a few examples. I've seen some really horrendous ones too. Here's one. The work done by force, W is equal to F times D, is a function of two variables. You may have a variable force, and you may have a variable displacement, okay? Their work is a function of two completely independent variables. Force and displacement, there's nothing in common with them, no units or anything. The volume of a right circular cylinder, V is equal to pi r squared h. That's a pretty standard kind of formula. But your radius could be a variable and your height could be a variable, and they don't have to depend on each other. So there's a volume depending on two. By the way, is pi a independent variable? Anybody? No, pi is a number. 3.1415, blah, 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 blah. It's not a variable at all. It's a number. Okay, so that's why they didn't include that. Or the volume of a rectangular solid, length times width times height, that's a function of three variables. Length has no dependence on... Oh, Josh is here, right? Yes? Okay.
I'm here. I just figured it out.
All right. Well, we'll put a red star on the day. You just figured... never mind. I didn't say that. Okay. By the way, perfect attendance. Way to go. First day online and everybody's here. We won't talk about how long you've been here, but we'll talk about that everybody got here. Okay, but here are the third three independent variables. Length doesn't have to depend on width, and width doesn't have to depend on length or height. The height doesn't depend on either one. No. Three completely independent variables. How in the world are we going to do stuff like this? The notation for a function of two or more variables is similar to a function of a single variable. Here are a couple of examples. If z, now this doesn't have to be necessarily a position z, but just some z, is some function of two independent variables. The x and the y, anything in parentheses here, are independent variables. We're used to just seeing a single variable there. Now we've got two variables, x squared plus xy. They don't depend on each other, independent. Or, even more so, w is a function of f of x, y, and z, three completely independent variables. X plus 2y minus 3z, function of three variables. Now, at least this one, I can make some kind of a cursory attempt at graphing, because I can visualize three dimensions. I can't graph three dimensions, but I can visualize it. This one is four dimensions, three independent dimensions and 1/4 dimension. I can't even become close to doing that. And that's why for three independent variables, all we can talk about are what they called surfaces. Where was that? Level surfaces. Level surfaces. I couldn't think of the word they use. Okay. So, here's the definition of a function of two variables. Pretty easy to extend to three. Let D be a set of ordered pairs, okay? Now, your domain, that's what D is. D is your domain. It's now not a value x on a number line. No, it's a set of ordered pairs of real numbers. So it's an area of a plane, okay? Not a number on the number line, an area of a plane, or not even a range of numbers on a number line. So it's a set of ordered pairs of real numbers. If to each ordered pair, x, y, in that domain D, there corresponds a unique real value, real number, f of x, y, then f is a function of x and y. So you see now, whereas before, y is equal to f of x, for any x, there's only one y. Now for any unique ordered pair, x, y, there's only one z, or f of x, y. The set D is called the domain of f. Now it's no longer a value. It's now an area, a region, okay? That is now your domain, set of ordered pairs. And the corresponding set of values of f, y, that's the range of f. Still just a single value there. For the function z is equal to f of x, y, x and y are called the independent variables. Both of them being independent, z is called the dependent variable. There can only be one z for any unique combination of x and y. Okay? If x, y was 3, 2, then there's only one z that corresponds to that. There could be a different z for 2, 3, but that's all right. That's a different ordered pair than 3, 2. Okay. So, find the domain of each function. Here's f of x, y.
We only have 4 minutes, by the way.
4 minutes? All right. I think we can do this first one. What would be any kind of a limit on that f of x, y for the domain of that function? The A one, yeah. Anyone see a limit on it? Any value you would have to avoid? Okay, a little louder. I'm going to guess what I heard. The x cannot be 0. Is that what I heard? Say yes.
Yes.
All right, good, good. Can everybody see why x can't be 0? So there's at least one feature. X cannot equal 0. We know that's got to be true. Anything else? Okay. Did I hear something like this, that x squared plus y squared minus 9 has to be greater than or equal to 0? Yes, I thought I did. Okay, now what can you do with that? Possibly add 9 to both sides? Oh yeah, that would work, wouldn't it? And that would tell us that x squared plus y squared has to be greater than or equal to 9. Is that right? Okay. Now, what does x squared plus y squared mean to you, especially in regards to 9? Let's forget about the greater than for a moment. Let's just focus on the equal 9. What does that describe? A what?
It's a circle.
That's a circle of radius 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. Centered at the origin, by the way, and it should be a better circle than that, or a better origin than that. Okay? So, what does it mean that x squared plus y squared has to be greater than or equal to 9? Isn't this it? Anything outside that circle, including the circle, because the equal sign there. Agreed? Okay. Now, that automatically excludes x equals. Oh, it doesn't either, does it? X equals 0 would be anywhere on the y-axis, wouldn't it? So it's anything on this side of the y-axis and outside the half circle, or anywhere over here outside that. So it's not just the origin, it's anywhere x equals 0. X equals 0 all up and down the y-axis. So what is the domain? I guess you would say something like this. Domain of this function f would be the set of all x, y, ordered pairs x, y, such that, you could either do a vertical line or a colon, either one, such that x is not equal to 0 and x squared plus y squared is greater than or equal to 9. Right? Okay. Now, how about the domain of this function, g of x, y, z? How are we doing on time? Oh, we're out of time, aren't we? Is that right?
Yeah, we're out of time.
Okay, so we're going to do 9b next time. Let's just take a real quick look and see what we got. If in the book, and we'll see this next time, in the book you see the circle there, and then the dotted lines that go above and below the circle, anything on the circle or outside of it. That. Now, one thing I didn't do, they did in the book, I put an open circle there so you don't think that part of the circle can be counted either. Okay. And theirs may look a little better than mine, but not much, right? Okay. I don't know if we did enough to do any homework exercises in this section. I don't think so. We'll just pick up and go from there next time. You got plenty to do on Chapter 12, including the test when I can get them to you. Like I said, it'll probably be the end of the day today at the earliest before I can do that, because I've got another class coming up right soon, and then yet another one this evening. So sometime after 6:30, well after 6:30, I'll probably be able to get you those tests. All right? All right, good deal. Have a good spring break. Someone wake Ryan up so he can have a good spring break, and we'll see you Monday. Bye-bye. Monday after spring break. He's almost dead. It looks like I think he has coronavirus. I mean, he's on his way out. All right. We will end it there. Have a good break. And be in touch through Blackboard or preferably probably email. Okay? All right.
I was hoping y'all couldn't even see me. What? I've been waving at the camera.
Okay. I saw. Oh, there's Josh. Okay. I don't recognize you without your hat on. Put your hat on so I can tell it's you. No, I'm just kidding. Okay. All right. We'll see you in 2 weeks. A little less than 2 weeks. All right. Take care.